I'll, offer my remarks. I won't do it justice, but I'll offer some remarks here. First of all, the best treatment that I've seen of the Yoneda lemma for me, well, okay. So one was a tutorial by John Baez, delivered personally. So that was really good this past summer. That was superb. But other than that, it's Eugenia Cheng's treatment in joy of abstraction. It's really, really good, chapter 23. And the truth is, I felt really bad because in the course I taught around that book, it's now 2 years ago, we didn't get a chance. We stopped just before that chapter. And I'd actually like to read it together. It's a worthy chapter, and I've read it, and it's awesome, and it really helps bring home the understanding. There is treatment of it in this particular book. I'm well known. I don't think we'll get to that section, but it's chapter 6, Yoneda lemma. So chapter 6 of Chief Theories for Examples deals with the Yoneda lemma. But the Yoneda lemma was central to some of the discussion for this chapter, chapter 2, and indeed section 2.4 in particular. And where it becomes of great relevance is in the context of representable. So these representable functors are these, we describe them as kind of these natural building blocks of presheaves or of C sets. They allow us to decompose any C set into a set of pieces. But one of the things that makes them so versatile is not just that they're kind of the natural building blocks, but the fact that they have this extraordinarily powerful property that they're kind of the natural way of searching for things. And I thought I had a nice slide here on this. Natural querying elements. But I actually had taken that slide, and I don't know where it went. But it's actually this image from Daniel Rosiak's book showing this one right here. You may remember this. If this is the representable point. So for this schema, this is not a schema. This is an indexing category. This is the schema. For that, there's two representables, one for this, one for that. Representable functors, one for each object here for a given presheaf or C set. In this case, it's a C set from this category to set. So there's a representable for L and a representable for V. And we identified what it was last time. Remember, the representable for this one included one of these and one of these. The representable for V just included one of these. So this is the representable for V. This is the representable for L. And this is where we derived it last time. And as shown in the book, these representables form sort of the natural queries against any C set here. So when I say natural, I'll explain that in a second, but they let us search out things with a certain very powerful property I'll talk about. So here, this is a C set. This is a C set. A C set has a certain number of points, a certain number of loops, a certain mapping between those loops and the points. So I think you'd agree this could be represented as a C set. You agree with that? Like we could figure out how many loops are there. Well, count them: 1, 2, 3. I guess there's 5 here, so that's 8, 9. So there's 9 loops. So this maps to a set of size 9. V maps to a set of size 4, right? And the mapping between the loops alpha, beta, gamma, well, it's just going to map alpha, beta, gamma here. Those are elements of the set of loops to the particular vertex here. It's going to map these ones to this vertex. Are we comfortable with this being a C set? So what I'm saying is this is a C set, this is a C set. And this is a C set homomorphism, meaning a natural transformation from this set to this set that finds all of these. It finds you. And this finds these. And I told you that these representables are the building block, natural building blocks, in the sense that every figure is built up out of these, combined with these. When I say combined with, not necessarily side by side, they're sometimes fused. They take the push out. So in other words, they glue them around this little dot here. Okay. And so any one can be built up here. And by finding them, we can find these natural building blocks. And here, there's some number of natural building blocks, right? Because it's 9 of them or something. Yeah, 9 of them. One here. And this is programmatic. Like we do this in CATLAB, right? We say, find me the homomorphisms from this, find me the homomorphisms from this, into this. And you might say, well, it's kind of interesting, but we could have shapes, we could have 2 loops here, and that wouldn't be a natural building block, but we could find it. And that's true. It would be a homomorphism between C sets. It would be a natural transformation. You could find that too. But what makes these special in terms of finding them? What makes them, in some sense, the natural queries for Hom finding is the Yoneda lemma. I'm presenting it. Probably some people will hate it, because I'm presenting it in a very sort of engineering sort of way. Things you could do with it that are useful. And the Yoneda lemma is like incredibly beautiful and powerful, and has all sorts of implications. But I'm a lily engineer, and so my mind goes to very practical uses. And one of them is we can find things fast. So look, this is a Presheaves. Okay, this is a representable for A. And I'd avoid getting too wrapped up in the COPs. I kind of screwed up the COPs when presenting this last time, but here they should be correct. But basically, this is a representable. And if we try to find a representable in any C set, in any or COP set, that's what we're doing right here. We're finding these representables in a C set. Yeah, do you agree? This is a representable, finding it in a C set. This is a representable, finding it in a C set. Do you agree? This is a C set. We just said this could be represented as a C set. This is a C set. Particularly simple C set. It's the representable C set, right? This one right here. V for L. And again, this is flipped around because it's COP, but if we try to find it, this is basically saying in this category where this is just an object, this is just an object, it's the category of Presheaves of C. So this is the category. In fact, it's right there. I don't even have to draw it on the board. Here's this category, COP set. There it is. Here it is. And this is just a dot there. This is a representable for B. You see that? This is a representable for A. Do you see that? Here's F. F is just a dot here. It's a dot in the C set category, COP set category. Why are we talking about that? Well, because we're dealing with the morphisms here. This morphism from this guy to this guy, from this C-op set, this presheaf on C, to this presheaf on C, what is that morphism? This morphism is a what? It's a homomorphism. It's a natural transformation. This is a functor. This is a functor. This is right. There's a functor. Right. It's a C set. It's a C op set, but you could call it a D set and make D C op. Okay. So this is a D set. This is a D set. Right. But I'll call it a C op set. I'll call it presheaf on C. So this is a functor. Is this a functor? It's a functor. All these are functors. All these are functors for the same category C. C op set. So look, if just to make this a little bit more clear, each of these is like one of these diagrams. This is one of them, right? This is one of these guys. If C were this indexing category, this is one of the diagrams that can result. But if we just had these three, it'll be one of those diagrams. Or if we just had this one, it'll be one of those diagrams. Those are all dots here. They're all different mappings from the same schema category to set. They're just different C-op sets. Do you agree with that? Are you okay with that? That each of those can be described as a C set, as a presheaf. And I'm telling you, like, remember we have these other categories just to get us away from making it too specific to the bouquet schema. Like, this is the schema for symmetric reflexive graphs. This is the schema for, where's my schema for graphs? Or for, this is symmetric graphs, right? Or this is my schema for dogs and people and homes, right? This is my schema for regular graphs. My point is, like, here C would be regular graphs. Here C would be this schema. Here C would be a schema for reflexive graph, whatever. Well, for any one of those, we could create a, oh, look at that. Look at this. For any one of those, we could create a C-op set. Do you agree with that? Like, sorry, for any one of those, we could define a category like this. And any, like, if C-op were the schema for graphs, each of these would be a graph, right? If C-op, so each of these dots, each of these objects would be a graph, right? And what would the morphisms be? Graph homomorphisms, which are natural transformations between the functors, yes, but they're graph homomorphisms. They're like squishing down of one graph to another, embedding it in the other, mapping multiple nodes to one node and the edges to the edges of that associated with that node. Are we okay with this idea? Like, so if C-op were the graph schema, each of these dots is a graph, directed graph. If C-op were the symmetric graph schema, each of these dots would be a symmetric graph. Would be all these vertices, and every edge from vertex X to vertex Y would have if you have two vertices X and Y, and every edge from X to Y would have a corresponding reverse edge from Y to X. Are we okay with that? If C-op were the bouquet schema, every map from every dot here would be a bouquet diagram like this, right? Would be a bouquet diagram. Note that this is a bouquet diagram. This is a bouquet diagram. But they're the special ones. They're the representable ones, right? And I'm telling you that in this category, where each of these is a dot, like for bouquets, each of these is a bouquet. Maybe this one here is this one. And maybe CA is this one. Those are bouquets. And these are bouquet homomorphisms, right? This is a bouquet homomorphism. What's shown here, right? I mean, we have this kind of finds where this is. So it's homomorphism here, finds one of these in here. And maybe it finds it in some degenerate way, like where, well, in this case, it's hard to imagine it being degenerate. There's not much room to be degenerate. But like if this were a graph, the representables for graph, do you remember the representables for graph? Like the edge, maybe the edge collapses down to be an edge from the same self node, right? Okay, yeah. So like maybe this is a symmetric one, and maybe as we map it over, this and this turn out to be the same, and same node X, and there's two loops. Well, they could be one loop, and this one maps to that, and this other one maps to that. And edge in that graph. So what I'm saying is like, yeah, there's these ones are bouquet homomorphisms. Yeah, the bouquet homomorphisms. Yeah, sure. But what Jeff was asking was what's so special? Well, he didn't ask it this way, but like, what's this thing with the Yoneda lemma? Well, the thing with the Yoneda lemma makes this powerful is look, the number of places we find, where's my nice picture? The number of places we find this representable for loop in our diagram, for any diagram, the number of places that we find it, I think I said this is the loop here. The loop, the number of places we find it, hey, come on. The number of places we find it is equal to F, the number of places we find it in a given bouquet diagram is equal to the number of loops in that bouquet diagram. Right? That's what that's saying. The number of places we find this loop is equal to the number of loops in it. The number of places we find a dot is equal to the number of dots. And you may say, well, whoop-de-doo, like, well, why do I care? Well, you care because you don't actually have to go through the work of finding them. You don't have to go through the work of searching them in certain cases. Like, if there's 0 of them, don't even bother searching. You don't have to do your work. You can skip looking for them. You don't have to look for them. So what I'm telling you is the number of, if this is the loop representable, if this is the representable for loop, this guy here. So this guy is, hey, come on, is this guy here. If that's what it is, hey, if that's what that is, and we have an F that's this diagram, the number of matches here will be the number of loops in this diagram, which is this, right? This F is a functor from C up to Z, and it maps A, in this case L, right? In this case L. It maps it into some set. Right? This is the number of L's in diagram F. right? Remember we said earlier, just a few minutes ago, we said like this diagram, we can encode it as a C set. Remember that? And I said like, if we encode it as a C set, L would map to some set, right? Do you remember that? V would map to some set. Remember that? And there'd be some mapping that says for each loop what its vertex is, right? Mapping from this set to that set. Say for each loop what its corresponding vertex, central void. What I'm saying is this set associated with L, to which this is a functor, maps L to a set of loops, those 9 loops. That set of size 9 means there's going to be 9 morphisms here from this to this. It's going to find this loop in it 9 different places in this here diagram. It finds it 9 places, so you'd have 9 here. It's going to find this one here, this dot, the center dot. It's going to find it some number of times. How many? 4 times. 1, 2, 3, 4. So there'd be 4 morphisms here. And one of the things that means is I don't even have to look. I don't have to go searching through. Maybe F is some god-awful big thing. And I don't have to go beating the bushes and like looking for all these loops or dots. I just look, okay, how many are there? If there's 0, I don't even bother. But more than that, here's the thing. Here's the thing. I said earlier that any C set can be composed of these representables. It's co-limit of representables. Remember that? Any C set, you can build it up as a co-limit of representables. This is what John Bies was describing. Any C set can be decomposed into these pieces, these natural building blocks, these Lego pieces out of which it's built up. Any C set is composed. Here's a graph. Here's a symmetric reflexive graph. There it is. Look at that. Look at that. You see that symmetric reflexive graph? Do you see that? These are its natural building blocks. John Bies just did that calculation. Actually, I think he had me do that calculation. But in any case, these are its representables. These are the natural building blocks. And I'm saying any symmetric reflexive graph is built up out of these. Okay, well, how do you build this one up? Well, you've got clearly one of those. By the way, there should be no, it's symmetric, so he's not even drawn. Okay, you got one of these. I don't know why he's drawn it here, but it's actually bidirectional. Yeah. So you got one of these. You got this one. That's another strut. You got this one. That's another strut. That's another one strut. Another one strut. Here, these ones. Okay, we got each of those, and we're actually, this is actually built up and has this in it. And so here we could decompose this given diagram into some of these diagrams. We could just take their color, we just glue these together around those points. So what I'm telling you is any picture can be decomposed into these representables. So they form, the fact that I can do wicked fast, or I could do searching for them in this clever means that really they're the natural things for me to keep track where they are in the, to keep track of them in the diagram. In other words, they're the kind of the natural pieces. If any complex structure you want me to search for is built out of them, and I can reason about those sub-pieces really fast, then maybe I could speed up that fast structure. So if a big structure is has a coproduct with one of these. I don't even have to search for those together. I could search for each separately, and the one that's a representable, I know immediately what its possibilities are, so I can reason about that. So the fact that these are the natural building blocks, and the fact that with the Yoneda lemma, we know the number of matches allow us to secure some opportunities for optimization of taking complex queries and decomposing them into simpler queries for some really important points. But this is the Yoneda lemma. It's saying that this is one form of the Yoneda lemma. It's saying, look, for any COP set category, for any Presheaves category, for any functor, so any sort of instance of that schema, associated schema, COP, for any instance of that schema, if I look the number of places that I can find a representable in that schema, it's equal to the number of things associated with the object of that schema. This is this deep relationship between kind of the data of the Presheaves on the one hand. This is kind of data of the Presheaves. This is actually links between, this is kind of maps between Presheaves, right? Like here. And yet there's this deep connection between them. The structure of this category, the number of morphisms from this to this, tells us what value f of a is, the number of values that go like this from these key representables. So these are incredibly powerful little tools. And in fact, I'm simplifying a little bit too much, or a little bit much here, because representables, something that's isomorphic to a representable would also be or to one of these Helm functors like this. Something that's isomorphic to it will also be considered a representable, because essentially anything that's mapped from this is going to have maps from this through there, because you could always go like this. So it's going to have a map. Yeah, Meti.
If you want to find a pattern, a special pattern in the C-set.
If you want to find a special pattern in a C-set.
The one is that we find the whole pattern in this C-set.
Right.
But instead of that, we can find the
right.
representative of this.
That's right.
Separately and after.
Exactly. Yeah. So yes, do reasoning like that. Yes. So take it into account. If you have this whole pattern, this complex pattern, and you want to try to find it, you may be able to find much more efficiently by reasoning about its constituent parts in terms of representables and realizing that wait a minute, this matching this pattern, maybe this big pattern, maybe it has a representable in it that you can immediately check. So it requires, maybe it's a coproduct with some representable where that representable is of a type that you can check the number of those things in the entire diagram that you're trying to match it into this big state of the ABM or whatever. There's none of those. And so you don't have to do the search of this giant thing anymore, because you know that a subpiece of it that's required is not there. That subpiece doesn't exist. It can't exist. And therefore, this entire pattern, you don't even bother searching for it, because you know it requires an impossibility. Because it's positing something as a piece of it that doesn't exist. And you can immediately check, does any of these exist? So by reasoning about its subpieces, which are going to be in common between different complex patterns. You give me complex pattern A, UJ gives me complex pattern B, Jeff gives me complex pattern C. All of those are going to be formed of these representables. And so if I can reason really quickly by virtue of them being of their constituent representables, if I can find shortcuts based on those, etc., if I can rule out needing to bother to search laboriously because I know it's positing something which doesn't even exist in the model, then I can speed that whole process up. And I think there's many more opportunities for optimization that take advantage of this common structure that we know it's built up out of pieces. Anyway.
Please go back to the reflexive directed graph and the representables.
Yeah.
Slide on.
This one.
Oh, you can see it. Okay.
Symmetric reflexive.
Oh,
This one.
yeah, this one. Okay.
Yeah. Yeah.
The representable vertex makes sense. The representable for edge.
The representable vertex is going to have.
Makes sense. One dot.
Yeah, that's right.
One vertex with the.
That's right.
But the E for the edge.
For the edge, let's
E
reason about edge. Okay, so I'll be with Jeff in just a second. Yeah. Representable for edge. Let's reason about the representable for edge, right? So that's what Y of E is.
Yeah.
Okay. So the representable for edge, we want to reason about, maybe we'll consider this as a C set instead of a C opset.
Mhm.
So we're going to consider all the things we can get to. That's right. All the ways we can get from E. So again, here, right? Here we're reasoning about all the ways we can get from an A to any other one, right? Each one is going to have the set of ways we can get. So if we're considered the representable for A, this Hom functor is going to map any object to the set of different ways you can get from A to that, right? The representable for A. So let's go back to this case with the that Uche was asking about. So let's consider what is this Hom functor for E going to map to? Okay, what is it going to map E to? Well, it's going to map E okay, you can get from E to itself this way. You can get to E to itself this way and then this way, but that's going to be the same. Okay, sorry. Yeah, I'm reasoning about these equations, right? So E. Let's do V first. Okay, going from E to V, what is it going to be? From E to V, you could go source R. Sorry. Okay, hold on. No. E to V, you can go this way and this way. And if you go back up, then going down again will get you exactly the same path, right? So E to V and going like this, it's actually going that edge. Yeah, so I'm thinking like there's two of these. This way, this way. I think the others just follow through. If you go like this, and then you go like this, it's the same as going by source, right? Yeah. And if you go like this and then go source, it's the same as target. So there's only two ways of getting from E to V. So there's two V's. let's go to, now let's try for E. Again, this is building on this, okay. E to itself. First of all, we can go with identity. And then we can go E inverse. And it would seem that that is going to be a different edge, and indeed it is, but that new edge has the property that if we take its source, it's the same as the target of the original edge. So this has two edges, right? Ujja, one going this way and one going that way, right? So there are two edges, the identity one and the one for E to get to itself. But they are such that for the identity one, its source is the source of the original edge, and the target is the target of the original edge. The new one here to get from E to E, its source is the target of the original edge, and its target is the source of the original edge. So it goes back the other way. So there's two E's and there's two V's. And look at this. Look at this, Ujja. If you do target and then you do R, wait a minute. No. If you do R and then target, it's identity on V. Because that's just taking the reflexive edge, right? And so each of these vertices has a reflexive edge around them. Yeah. And each of these vertices has this, yeah. And so for V, you also have that reflexive edge. So I think this is correct for this. And I think this is built out of those pieces. But this requires co-limit of representables. Yeah. Okay, Jeff. So you wanted to ask it.
Copying down some text that isn't properly formatted, I can read it in.